Leah here from leahforsci.com/MCAT, and in this video, we're going to look at phase 2 of glycolysis, which is the payout phase. In video 1, we looked at the first 5 steps of glycolysis, where glucose was phosphorylated to glucose 6-phosphate, isomerized to fructose 6-phosphate, phosphorylated again to fructose 1,6-bisphosphate, broken into 2 pieces, dihydroxyacetone phosphate and glyceraldehyde-3-Phosphate, and then converted all of the dihydroxyacetone phosphate to even more glyceraldehyde-3-phosphate. So where do we stand so far? We have 1 molecule of glucose sitting at 2 molecules of glyceraldehyde-3-phosphate with a total investment of 2 molecules of ATP. So far we've done a lot of work and put the energy in, but now that we're in phase 2, we finally get to the payout phase where we expect to see some energy coming out of these molecules. As a reminder, we broke the molecule in half. We converted DHAP into glyceraldehyde-3-phosphate. So for every reaction moving forward, remember that we have 2 molecules reacting per molecule of glucose. So when we look at step 6 and we see that glyceraldehyde-3-phosphate reacts, remember that it's 2 of them. In step 6, we see the first release of energy when glyceraldehyde-3-phosphate is converted to 1,3-bisphosphoglycerate, or simply 1,3-BPG. 1,3-bisphospho tells us we have a phosphate group on carbon number 1 as well as carbon number 3. Even though this reaction adds a phosphate group onto the molecule, we're not using a kinase in this case. We're actually going to react G3P with NAD+, along with an inorganic phosphate that happens to be available in solution, and this is the phosphate that we put on the molecule. The enzyme that catalyzes this reaction is called Glyceraldehyde-3-Phosphate dehydrogenase. Yes, the name is a mouthful, but this is simply G3P dehydrogenase, which tells us that it's an enzyme that acts to dehydrogen, to remove hydrogen. What hydrogen are we removing? Notice that in the reactant, we have a hydrogen atom with 2 electrons binding it to carbon, and in the product, both the hydrogen and both of its electrons are gone. That means we're losing an entire hydride ion, which is a hydrogen, 2 electrons, and a negative charge. Why is this important? Because this right here is the one redox reaction that we see in glycolysis. Remember that in a redox reaction, something can be oxidized by losing electrons, and something else will be reduced by gaining electrons, in which case here we have an NADH plus an H plus. But wait, that doesn't seem to add up. I said we're losing a hydride, an H minus, and yet in the product I'm giving you 2 H's with a positive charge. What's going on here? How does NAD plus gain a hydrogen and then give us 2 hydrogens in the product? Very simple. Remember that hydrogen is the smallest atom, and it contains simply 1 proton and 1 electron. If I have a molecule that in addition to the molecule itself I have a proton, what I'm really looking at is a hydrogen without its electron. So if I take that proton and I add an electron to it, I get a hydrogen. So I have NAD, a proton, and an electron. That takes care of the electron. The proton is what we see over here. H plus is simply a proton, but instead of saying plus proton, we're saying plus H plus. And the other electron winds up on the enzyme. I'm sharing this not for you to memorize these details, but rather to understand what happened and to understand why this is a redox reaction. For more on redox on the MCAT, make sure to watch my oxidation reduction video series linked below. We said this is the first energy harvesting step. But how does getting an NADH and an H plus help us? Extracting the electron here allows us to get even more energy out of it later through processes like the Electron Transport Chain, which we'll cover in other metabolism videos. But for now, let's move on to step 7 and look at this very high energy 1,3-BPG. As a reminder, the P in the circle represents a phosphate group, but don't forget that each phosphate has a negative charge. And having two phosphate groups with a negative charge so close to each other makes this molecule very unstable. And when a molecule is unstable, it is unhappy and therefore very reactive. And that means it's looking to get rid of this high energy so it can become more stable, which is convenient because we have lots of ADP floating around in solution. In addition, we grab an H+, dump a phosphate onto that ADP, which gives us our first ATP out of glycolysis, in addition to a molecule that is now missing a phosphate group and has just an O- on carbon number 1. What we have here is a carboxylate, because it looks like a carboxylic acid, but it's missing that hydrogen atom. 1,3-BPG was converted to 3-phosphoglycerate, or simply 3PG. This is a very important reaction. Notice that we have ADP, and without having to go into the mitochondria for the electron transport chain, we managed to get a high-energy ATP out of this reaction. This step is called substrate-level phosphorylation because we're getting phosphorylation. We're getting an ATP directly at the substrate level, not to be confused with oxidative phosphorylation, which happens on the electron transport chain in the mitochondria. The enzyme that catalyzes this reaction is called phosphoglycerate kinase because it's a kinase, a phosphate transferring enzyme that removes a phosphate group from glycerate. But wait a minute, doesn't kinase put a phosphate group onto a molecule? Here we took a phosphate group off the molecule. Well, actually, we can look at this two ways. Number one, as we saw with the aldolase, the reverse reaction is getting a phosphate added onto the molecule. Or think of it as, yes, kinase is transferring a phosphate onto a molecule, but not the molecule we're looking at. We're transferring the phosphate onto the ADP. Now that we have a more stable molecule with just one phosphate group on 3PG, we want to convert it into a form that is closer to pyruvate, our ultimate goal, which is exactly what we do in step 8. The phosphate group ends up on carbon number 2, and carbon number 3 gets an OH, forming 2-phosphoglycerate, or 2PG. Take a look at what happened here. We had a phosphate on 3. We got a phosphate on 2. We had an alcohol on 2. We got an alcohol on 3. This looks like a simple, straightforward isomerization reaction, but the enzyme phosphoglycerate mutase is not a straightforward isomerase. Phosphoglycerate, because it's moving the phosphate group on a glycerate, but mutase, it's creating this isomerization reaction not by moving it, but rather by first mutating the molecule. What? The intermediate for this reaction still has the phosphate group on carbon number 3, but it also has a phosphate group on carbon number 2. The mutase works by adding a phosphate group on carbon 2 and then removing the phosphate group from carbon number 3 to form a very stable intermediate called 2,3-bisphosphoglycerate. It's important to point out that this is a stable intermediate. In fact, 2,3-bisphosphoglycerate, or 2,3-BPG, should sound very familiar if you've already studied hemoglobin. Think about it. 2,3-BPG is a molecule that influences hemoglobin to be less effective at binding oxygen. Why would a glycolysis intermediate have anything to do with hemoglobin? How are they connected? Actually, very much so, if you think about what's going to happen next. Even though not every molecule of glucose that undergoes glycolysis will go into the Krebs cycle and then the electron transport chain, a lot of it will. And once we start the electron transport chain in the mitochondria, we're going to need a lot of O2 molecules, because without O2, the mitochondria stop working. So if we know we're revving up the machinery, we're sending a lot of pyruvates down the chain, shouldn't we start telling hemoglobin to prepare to get us all that oxygen so that we can have energy? And that is how hemoglobin connects to glycolysis, because this stable intermediate 2,3-BPG doesn't all get converted to pyruvate. Some of it escapes, gets out of the cell, and tells hemoglobin to get working. But the rest of it are converted into 2PG, which is important because this takes us one step closer to the goal. In step 9, we're going to remove a water from our 2PG molecule by removing an OH group from carbon 3 and a hydrogen from carbon 2, and replace it with a pi bond between carbons 2 and carbon 3. This gives us a phosphoenol pyruvate. This molecule is also called PEP or PEP, and of course a molecule of H2O. The enzyme that catalyzes this reaction is called an enolase because the product is almost our pyruvate molecule, except that it has a phosphate group and it's got an enol. The phosphate group is still sitting on carbon number 2, and the enol is hiding right over here. Remember that in order to bind to a phosphate group, we have an oxygen in there. The phosphate group is an OPO with another O and another O. And that right there is really an alcohol bound to the phosphate group next to an alkene. And if you recall, anytime you have an alkene plus an alcohol on the same carbon atom, you have what's called an enol. This right here is the enol explaining the enolase enzyme, an enzyme that forms an enol. Students often ask if this is another redox reaction, and the answer is no. While we are removing a hydrogen from the molecule, we're removing an entire molecule of H2O. One of the carbon atoms gets oxidized, the other gets reduced, but the net change on the molecule is neutral. That means there's no net oxidation or reduction, making this a non-redox reaction. We are so close to the final step that even the name of our reactant, phosphoenol pyruvate, already has our final product in there. We can sense the pyruvate coming. Thing is, pyruvate does not have a phosphate group, so let's get rid of it. To do that, we find an ADP and an H+ that are freely available in solution. We get rid of that phosphate group and dump it onto the ADP to give us a high-energy ATP, which you'll recognize is our second substrate-level phosphorylation reaction. The resulting molecule has a carboxylase for carbon number 1, a carbon double-bound O on carbon number 2, because in addition to removing the phosphate group, we also moved the pi bond. So just think that this pi bond jumped up over here, giving us a second bond to oxygen, and the third carbon that had 2 hydrogens now has 3 hydrogens because it lost its pi bond. And this right here is the long-anticipated pyruvate final product. Given the big release of energy in the final step, this is a one-way, irreversible reaction where the cell has to decide, am I ready to turn my phosphoenol pyruvate into pyruvate, or do I have to reverse this reaction to avoid having a buildup of pyruvate molecules? This reaction is catalyzed by the enzyme pyruvate kinase, because it's a kinase, an enzyme that adds a phosphate group, in this case from the molecule pyruvate, not to the molecule pyruvate. Instead, that phosphate group gets transferred onto the ADP. Whew, that was a lot. But if you're feeling overwhelmed, take a deep breath, take a step back from all the crazy names and structures, and actually review what happened here logically. But first, make sure you give this video a thumbs up, subscribe to my channel, and hit that bell icon so you don't miss out on any new videos. And then join me in part 3, where we review glycolysis from a much more simplified perspective, where our focus is going to be on what is happening and why, rather than looking at all the details as we did in parts 1 and 2. You can find this on my website along with the glycolysis cheat sheet by going to leahforsyth.com/glycolysis or clicking the link below. Again, that's leahforsyth.com/glycolysis.